Hello, this is Math 2520, and this video will be over section 8.7. And in this section, we're going to talk about some more methods of integration. One of the main helpful things is integration tables that have specific integrals that you can follow that have already been kind of proven and done. So that way you don't have to reinvent the wheel and redo a proof over and over again. So usually in the back of a textbook, there's integration tables. You can also look them up online. I mean, this isn't necessarily something that can be easily put on a test, but it's something that in real life you can do. I have multiple degrees. One of my degrees is in physics, and going into physics, when we get an integral that we have to solve, usually it's, well, let me see if I have an integration table. Not me figure out how to do all the old mathematics that I've learned. All right, so let's just get into this. So if we have the integral from 0 to pi over 2 of cosine of 5x and cosine times cosine of 2x dx, we can look at this as in an integration table where cosine of mx and times cosine of nx dx equals sine of m minus n x over 2 times n minus n plus sine of m plus n times x over 2 m plus n. Again, this will be something you find in a table. Right, and so you can actually, a lot of times just look up a table and there'll be a list. And there's definitely one in the back of the book. So here our m equals 5 and our n equals 2. So we can plug that in. And so this is already doing the integral. Now we're plugging things in. So we'll have sine of 5 minus 2 x. Actually, no, just do that. So we'll have sine of 3x, 5 minus 2x, over 2 times, and then 5 minus 2 is 3, plus sine 5 plus 2, which is going to be 7x, over 2 times 7. And so I'll simplify this more. Sine of 3x over 6 plus sine of 7x over 14. And then the integration is done. We can put our limits here, 0 to pi over 2. So integration is done. That's looking in the table is in a sense doing the integration. And so we now evaluate our limits. So sine of 3 pi over 2 over 6 plus sine of 7 pi over 2 over 14 minus sine of 0 over 6 plus sine of 0 over 14. And sine of 0 is 0 in both of these cases. Right. Sine of 3 pi over 2 is negative 1, so you got negative 1/6, plus, and then sine of 7 pi over 2, go around, pi over 2 is at 9 degrees, 3 pi over 2 is at 270, and then you go 4 pi over 2, 5 pi over 2, 6 pi over 2 is at pi, so this is also a negative 1, so negative 1/14. And then we can find a common denominator here. So negative 14 plus negative 6 here, and 14 times 6, 84. So negative 20 over 84, which if you divide that by 4, you get negative 5 over 21. And that's your final integration. Right. Next one, and the integration tables, sometimes they can look confusing because they'll have just random letters. And so you have to kind of pinpoint how it matches and what's what. So if we have the integration of 0 to 1 of square root of x minus x squared, we can find this in the integration table, square root of 2a minus u squared dx. Or in this case, u is x, and then 2a would be equal to 1. So a equals 1/2. And so now, I don't even know what the first part of this. This is equal to u minus a over 2 square root of 2au minus u squared plus a squared over 2 inverse cosine of a minus u over a. And so we plug in what we have for u and we plug in what we have for a. So u is x, so x minus 1/2 over 2 square root of 2 times 1/2 x minus x squared plus 2a squared over 2 cosine inverse of 1/2 minus x over 1/2. Right, and then again, this is going to be from 0 to 1, so we can't forget our limits. Right, we'll simplify this sum. Not sure if there's a lot of simplifying we can do. Let me save some space here, though. I'll simplify it in within this. So 2 times 1/2, that is just 1 times x minus x squared. 2 squared is 4. A squared is squared. So this becomes squared, and then this becomes just 2. Because that 2 divides out. And I'll leave the inside of these the same. Right, so now let's evaluate the limit. First limit 1 minus 1/2 over 2 square root of 1 minus 1 squared plus a is 1/2. Why did, oh, hold on. I just caught a mistake. Let me write this again. So we have a squared over 2. A is 1/2, so this is 1/2 squared, not 2a. And so 1/2 squared is 1 over 4, so this is going to be 1 over 8. Okay. Alright, so now we have 1 over 8 inverse cosine 1/2 minus 1/2 over 1/2. So that's the first part. Then minus the second limit is 0. So this becomes 0 minus 1/2 over 2. 0 minus 0 squared plus 1/8 cosine inverse of 1/2 minus 0 over 1/2. Alright. So let's see what goes to 0 this whole square root in the second part is going to be 0, which makes this whole thing 0. Here we're looking at the inverse of 0. And okay, let's just simplify this up. So actually, hold on. This is going to be 1 minus 1 squared is 1 minus 1, which is 0. This whole thing is also 0. Alright, so the whole thing is going to be 0. So we'll end up now with 1/8 cosine inverse of 0 minus 1/8 cosine inverse of 1. And for this, we'll look at what these angles are. So 1/8 cosine of 0, I'll look at this within 0 to 2 pi. Is pi over 2 or 3 pi over 2. Right, so it's going to be intervals of pi over 2 plus k, k pi, k. I'll do k pi. K pi. Well, k is just where you are on the circle there. And then this one will be 1/8. And what gives 1 is anything that's every 2 pi, so 2 pi k. And so we can write this as pi over 16 plus k pi minus pi over 4 k. Alright, so k pi and pi k are the same thing. So this is 1k minus 1/4, so it's 3/4 k. So pi over 16 plus 3/4 k pi. That'll be your final simplified answer. Even with the integration table, some of these integrals can take some time. Alright, so next one, natural log of 1 plus square root of x over square root of x. Alright, so here we actually don't need an integration table. Alright, so sometimes you don't. We can do this in just a u substitution. And actually it's not too bad. So let u equal 1 plus square root of x. So du equals 1 over 2 square root of x dx. Alright, so the integral becomes, see, natural log of u, and we'll have a 2 out front here. We'll have to multiply this by 2, so we have what's under there. But then it's just 2 du. I accidentally switched colors, but that actually works out. Alright, so 2 natural log of u du. We're integrating natural log of u. Okay, so this is why the integration table comes in. So we can pull the 2 out. We'll have integration of natural log of u du. This is going to be equal to 2, and then the integration of natural log of u is u natural log of u minus u, and then plus c because we have no limits. Right, and so now we let u equal what it did. So 1 plus square root of x natural log of 1 plus square root of x minus 1 plus square root of x plus c. Okay. So the integration I will use in the table is the integral of natural log of u equaling du equaling u natural log of u minus u. Right, so some more of these. The integral of xe to the ax, once it stops saving, I'll write it. That is going to be equal to 1 over a x e to the ax minus 1 over a integral of e to the ax dx. Sometimes an integral table has an integral that still involves another integral, and it just makes the integral that you have to do a little bit easier to do. So in this case, a equals 5. So we can make this become 1 over 5 x e to the 5x minus 1 over 5 integral of e to the 5x dx. This formula, this will have been found with integration by parts, something we've already done. But it's in the integral table, so we don't have to keep doing integration by parts every time we do it, which you should be able to kind of tell that's the case. All right, so now we'll integrate e to the 5x, and when we integrate e to the 5x, we'll get 1 over 5 e to the 5x. And so simplifying this, 1 over 5x e to the 5x minus 1 over 25 e to the 5x, and then plus c. Since we integrated, we shall have plus c's everywhere here. Alright, so square root of x squared plus a squared dx. We can find that in an integration table. It actually wouldn't look that way though. It would be a squared would be first. This integral is going to be equal to x over 2 integration of a squared plus x squared plus a squared over 2 natural log of x plus square root of a squared plus x squared plus c. And in this case, a equals 2. Okay. This would be something that, again, you will see it in an integration table, but it's also, if you recognize it, we've solved things like this with the inverse trig substitution, and we always seem to end up with a natural log of something. So that should be recognizable. All right, so we'll insert what a is equal to. So I have x over 2, 4 plus x squared plus 4 over 2 natural log of x plus a squared is 4 plus x squared plus c. And then just to simplify this so I don't have to rewrite the whole thing, 4 over 2 is 2. And that's your final answer. So we could look up, you know, and we kind of already done integrations with tables before. When we look up antiderivative to inverse trig function. So from a table, we may find that the arctangent of x dx is equal to x arctangent of x minus 1/2 natural log of 1 plus x squared plus c. And then that's what we find in it. Now that's all we're trying to integrate, so we have everything here that we need for the integration to be final. This next one we'll integrate. The integral can be solved using the identity sine squared x equals 1 minus cosine of 2x over 2. Okay. Or we can find it in our integration table. So in an integration table, what you'll find would be 1/2 minus the integral cosine 2x over 2. Okay. This is literally, I mean, sine squared is this, so we're switching it to this, and then this is just the fraction broken up. That would be dx. By hand, we would have to integrate both of these, so 1/2 x, and then this side we'll have integration of cosine of sine, so sine of 2x, and then have to divide by 2, so over 4 plus c. Last one, if we are looking at integrating sine to some n power over cosine to some n power, right? We've done problems like this. So what we would do is, let w equal cosine of x, dw equal inverse sine of x dx. And so we'll have integral of 1 minus cosine squared x sine of x, and we're solving this one here. Cosine squared x dx. And so we can adjust this form so it's cosine squared x minus cosine to the 4th x by distributing the cosine, but not distributing the sine x dx, because that's going to be part of our dw that we're substituting in. And so we'll end up getting integral of negative w squared minus w to the 4th dw. Or we can write this integral of w to the 4th minus w squared dw. And then that becomes w to the 5th over 5 minus w to the 3rd over 3 plus c. And then we let w equal cosine again. Okay. And that would be our final answer. Alright, so that's some more on integrals. In the next section, we're going to get away from a little bit with different methods and look a little bit at some other important things with integrals. See you then. Bye.